Alright, so in this video we go over section 2.2, rate of change and derivatives. So this section is going to be a follow-up of what we did in the previous section, which was the limit. We are going to use the concept of limit to come up with the concept of derivative. The derivative ultimately will be the slope of a function at a given point. Well, so where have we heard about the slope? So we heard about the slope back in intermediate algebra when we were given 2 points that lie in a line. We found the quotient of the difference of the y's to the difference of the x's. In other words, like the rise over run, and that was the slope of the line. And in some case, well, for the cases of for all of the straight line, the slope is always the same at the same point because it's a straight line. However, when it comes to trying to find the slope of other functions like a parabola or another curve, the slope at any point it's not the same, and the rise over run formula is not going to be it's not going to be useful. It's not going to work rather for our purpose. So first of all, let's look at what the average rate of change is. So for a function y f of x equals f of x, the ratio delta y over delta x, which is y2 minus y1 over x2 minus x1. Well, where do we get that y2 and that y1? By evaluating the function f at the given function f at x2 and at f1, at x1 rather. And of course, x2 equals x1. So this formula is very reminiscent of what the slope, of that of the slope. So how are we going to use this? Well, first of all, let's go back to what we learned back in algebra. Well, so we even have a picture that will confirm the results that we are about to obtain. So we have the function y equals to x plus 1. Let's find the average rate of change of y with respect to x, as x changes from x to 3, and then we are going to repeat the process for x changing now from 1 to 4. Alright, so so we need a y2 minus y1. That y2, we get it by evaluating f of x2, which is in this case, let's do it first. Okay, let me do for x equals 0 to 3. Okay, let's do that one first. So y2 equals f of x2, which in this case is f of x. Oh, wait a minute. Let me do it the other way around. Hold on. So let me just do y1. Yeah, let me start with the first one and then with the second one instead. Yes, just to follow the order. So this will be 2 times our x1, which is 0, plus 3, which is going to give us, no, not plus 3, it's actually plus 1. Sorry, I'm making a couple of mistakes here, but yes, I'm being aware of it. So, and then y2, which equals 2 times 3 plus 1, which equals to 7. So we are ready to compute delta y over delta x, which is y2 minus y1 over x2 minus x1, where y1 is 7, y2 is 7, y1 is 1, x2 is 3, and x1 is 0. And this delta y over delta x will be 6 over 3, which reduces to 2. But what is this ultimately? Well, from the picture here, we got the graph of the function y equals to 2x plus 1, right? And we are essentially what we're doing is finding the slope of the line that passes through these 2 points, 3, 7, 0, 1. So we got for delta y, which is 6 in the numerator. Okay, so I need a different color, 6. And delta x, which is 3. All right, so that's what we got. So that's the slope of the line. That's the rise over run, or to 6 over 3, which reduces to 2 over 1. Now let's repeat this process for x changing from 1 to 4 and see what we get. So because this is a straight line, we should get the same slope. Let's verify that. Well, of course, this is a 3, and y2 equals 2 times, let me fix that. This is supposed to look like a 1. Yep, and 2 times 4 plus 1. And that's going to be 5 plus 1, which equals 6. And we're ready to compute delta y over delta x, which will be y2. Again, well, I'm not going to write the formula, just going to go with the quantity 6 minus 3 over 4 minus 1, which is 3. It's actually not 3. This is supposed to be 9. That's 6 over 3, which equals to 2. So again, because in this case we are coming up with, we're working with a straight line, the slope at this point and that point, between those 2 points, is the same slope at the point where 1 and 4. Notice the value of the slope is the same. I'm going to do that over here. The same rise, the same run. Now, like I mentioned before, when it comes to extending this concept to finding the slope or the average rate of change to a function that is no longer linear, like the one in the next example, well, let's see what we're going to get about it. All right, so let's see. So let's y equals the square root of x. Find the average rate of change of y with respect to x as x changes from 0 to 4, and then as x changes from 1 to 4, and then compare both results. Okay, so again, let's do for x equals 0 to 4. Let's do the calculations. So y2, or rather y1 equals the function, the square root of 0, which is 0, and y2, which is, in this case, well, the square root of 4. Where am I getting this 4 and this 0? Well, in this case, this is x1 and x2. And then from here, well, let's simplify. The square root of 4 is a nice number. It's a perfect square. Square root of 2 over, the square root of 4 is 2. So now we're good to go and compute delta y over delta x. Again, that's y2 minus y1 over x2 minus x1, where y2 is 2, y1 is 0, x2 is 4, x1 is 0. This reduces to 2 over 4, which reduces to 1/2. So that's the average rate of change of y with respect to x, as x changes from 0 to 4. Let's look at what happens for the other situation when x changes from x equals to 1 to 4. And so y sub 1, so y1, which is the square root of 1, which equals to 1, and y2, which equals the square root of 4. All right, let's see what happens. So that's a 2. And delta y, delta x, or delta x is y2 minus y1. That is 2 minus 1, or it's actually, yeah. And that's x2 minus x1, which is 4 minus 1, which is going to be 1 and 3. And if you compare these two values are no longer the same. So what we're doing essentially is finding the average, well, the average rate of change, which is like the slope, or the average slope between the points where x equals 0 to 1 and 0 to 4 and 1 to 4. However, in this case, well, the two numbers were different as opposed to the case in which we had the linear function. When we compare, these two values are the same because in this case it's a straight line. The slope is always the same. Rise over run is always the same, regardless of the pair of points that you get. Here, the sort of rise over run, the steepness of the graph is not going to be the same. For example, if we look at the graph of square root of x, which looks something like this, we have the point where 0 and 4, and then the point where 1 and 4. So over here we have one secant line containing the 2 points, which has a slope of 1/2, and over here we have another line with a slope of 1/3. And in this case, it's not the same slope. And we can analyze, of course, many functions do the following. For example, the case in which the function is y equals x cubed. And let me show you an animation here. So for example, here we have the function y equals x cubed, and the slope, the rise over run, is no longer the same at any point as it is for a straight line like we did in the first case, in the first example. Notice at different points, the steepness, or the rise over run, if you will, is different. See how it changes when as I drag the line, the point right here that holds the line. All right, so let's do an application dealing with average rate of change. So a ball is dropped from an airplane, and the distance d, which by the way, this distance I didn't write it down. This one should be in feet. In feet, that falls in t seconds, is given by the function d of t equals 16 t squared. How far does the ball fall during the first 3 seconds? So, well, just to do this, all it takes is evaluate the given function at t equals to 3. And that's going to give us 16 times 9, which equals 144 feet. Okay. Now they're asking us, what is the average velocity of the ball during the first 3 seconds? And in this case, what they're asking us to find or to compute is the average rate of change, where delta, instead of delta y over delta x, we're going to do delta d over delta t. And if you look at the two quantities that we're comparing here, or that we finding the ratio for, is distance over time. You know, that's how we find the velocity of any particle. You know, distance over time. And in this case, we get that this distance by finding the average rate of change. In this case, let's call it d2 minus d1 over t2 minus t1. But where are we going to get this d2 over d1, etc.? Well, I'm going to do this on the side. By the way, this is too big. Let me make it a little bit smaller. And no, it didn't work. And Control C. Right. So let me move this over here to do the calculation here. So what we're gonna do is find the distance at the point where during the first 3 seconds, that is from t equals to 0 to t equals to 3. In other words, d1 will be actually, well, let me actually denote what d1 is going to be first. So t1 equals to 0 and t2 equals to 3. So when we evaluate this, add up to get d1, which is the evaluated at 0, that's a 16 times 0 squared, which is going to be 0. And d sub 3, no, d2 actually, which is at 3, 16 times 3 squared, which, well, we already did this calculation, which is 144. So we're going to get 144 minus 0 over 3 minus 0. That's going to give us 144 over 3, which equals, in this case, 48. And for the units, well, we are relating units of distance over time. That's feet per second. All right. So this is a problem where we find the average velocity. Now, how fast is the ball traveling when t equals 3? So now in this case, we're not being asked for the average, but we're actually being asked for a specific time. And then in this case, so far, cannot tell. So this one we cannot tell. We need instantaneous velocity as opposed to average velocity. So we need the instantaneous velocity. We need to know how fast it's going at a specific time. And then in this case, this formula is not going to help us find that value. So this is what we're going to do. So we're going to compare average rate of change versus instantaneous rate of change. Well, so let's start with the fact that the slope of a curve at a point AB is exactly the slope of the tangent line to a curve at that point, right? So that's this is the picture that we are going to use as a starting point to construct the idea of the derivative, right? They also call it instantaneous rate of change. All right, so let's consider x comma f of x or xy. Typically, well, we call f of x, we call it y as well. So let that be any fixed point on a curve, and x plus h comma f of x plus h, another point. And then the difference quotient in the slope of the secant line through these points will be given, well, so this is basically our y2, our y1, x2, and x1. Basically the same as what we did with the average rate of change. However, we are going to use this idea and the fact that we are going to eventually go from secant line, which is what we did in the previous examples, getting the slopes of the secant lines, to get the slopes of the tangent lines. So we are going to construct that idea, and here is a picture I have here. There's a picture I have here that gives us a graph. Well, the graph of the function doesn't really matter, and in this case, well, we have this point. Instead of calling it C, well, from the applet I got this, they use the letter C, but it's ultimately X. And here we have another point, X plus H. And how so? Well, this point is H units away from C, right? And what we're going to do from here, well, it's notice, okay, this line that is highlighted that is this line in green, I'm going to highlight it as well. This line is passing through two different points on the graph of f of x, this point right here and this point right there. So this is the slope. Well, actually, secant line, not a slope. Well, of course, it has a slope. Secant line. All right. But then we also have a tangent line. This one that I'm highlighting here with purple. And this one is going to be a tangent line because it only touches only one point as opposed to the secant line, which touches 2 points on the graph of f of x. All right. Well, the idea is that I would like to do the following. I would like to drag this point right here closer and closer so that the secant becomes tangent. That is, I would like to reduce this distance x plus h and eventually have this h equal to 0. Well, right here on paper, well, on the screen like this without an animation may be hard to visualize. So I'm going to show you another applet here. So for example, and I have it here, let's see, I think I had it over here, and let me show the secant line. Well, so this is what's going on here. I have this C and C plus H, which, well, in our definition is X and X plus H. So I'm going to drag this in such a way. So notice I'm going to make it even further. It's still a secant line. And as I get this closer and closer and closer to C, that green line, well, right now it's still a secant because it's still touching 2 points. But when I get this distance 0, actually, when these 2 points are at the same position, C and C plus H, that's what we get in this case, the tangent line, right? And well, in this case, okay, let's go back to our notes here. So, oh, by the way, the slope right here, let me erase this. Let me erase all this just to show you how are we going to define that slope. Well, so this is x, and this is x plus h. This point is f of x, so that's the y coordinate, and this point right here will contain f of x plus h. So if we find the slope y2 minus y1 over x2 minus x1, well, this will be f of x plus h. minus f of x, that's the y, this is the y2, and this is the y1, over x2, which is x plus h, minus x1, which is x. Well, in this case, notice how these two x's go away, leaving us with f of x plus h minus f of x divided by h. So let's go back over here to our notes. So again, this is our f of x plus h, which is our y2 minus f of x, which equals to y1, over x plus h, which is what I did, which is what I just wrote on the graph, right? And of course, this is how we relate that average rate of change to which calculates the slope of the secant line. But now we are going to come up with an expression that also finds the slope of the tangent line. However, in this case, f of x plus h, it's the same expression with a little extra. I'll show you what that little extra is in a second. Well, coming back to the animation. So what I'm doing is making this distance between the 2 points that I'm dragging. So here I'm making it away from the other. I'm making it closer. How close? Very, very, very close. In a way that the distance between them is, well, nothing. It's 0, right? And we managed to get that by calculating a limit and having that h equal to 0, right? So going back to our notes, so yes, it's the same expression. However, in order to get the slope of the tangent, we have to have the limit to approach to have h approach 0, right? And that's the definition of the derivative. Now we have an expression in terms of a limit that helps us find the instantaneous rate of change. All right, so um, let's look at an example. But I think this is going to be a good point to quit, and let's look at another video.